Okay, so continuing where we last left off, we were discussing this theorem, and this theorem is very important in the topology area. It basically tells us, you see, what we're aiming towards is we want to collect a catalog of what are the open sets. Let me quickly remind you what an open set is. So if we have some set here, let's call him A. Then a set A is open if it is equal to its interior. So the interior of the set is equal to A. That means every single point of this set is an interior point. So what's an interior point? Very easy. So we say X is an interior point of A if you could find a specific radius, let's call him epsilon, such that the neighborhood, remember how we write that? The neighborhood or the open ball centered at X of radius epsilon is completely within the set A. If you could find such a radius to wrap a neighborhood around it that falls within A, we say X is an interior point of A. Interior point of A. And now a set is said to be open if every single point is an interior point. So every single point you can do that. And we saw that the open interval AB is an open set. Okay, and over here, A and B are finite. Okay, A and B are finite numbers. For example, 0, 1. Okay, so these are the open sets. Now the question is, okay, if I know that the open interval is an open set, can I use this, or if I have a list of open sets, how could I make more open sets from it? And that was the last thing we discussed, and it's given by a result that says, well, the first one is that the empty set and all of the real numbers are open sets. Okay, and the second one is saying that if you have any number of open sets, countable, uncountable, finite, infinite, it doesn't matter. If you have any collection of open sets and you union them together, you will also get an open set. So I see students usually abbreviated by this. They say the arbitrary union of open sets, arbitrary union of open, I don't think they put an S. Arbitrary union of open sets is open, right? So if you want to union in open sets, you got an open set. Now, if it comes to intersecting open sets, if you want to make an open set and you're intersecting open sets together, you are only allowed to do finite intersection. So the finite intersection of open sets is open. Okay, so arbitrary unions, open sets, open. Finite intersection of open sets is open. Okay, so that was this theorem, and we went through the proof of it last time. So now that we know, given a list of open sets, now that we know how to construct more open sets, we could, for example, talk about these type of intervals. So A comma infinity. Now we know the interval AB is open. But what if the right point is no longer finite? What if it's A all the way up to infinity? It turns out that this interval is also open. And the reason for that is because we could write this interval as the union of these finite intervals, A comma A plus n. Okay? And this is a arbitrary union. Each of these A comma A plus n is open. So this is the arbitrary union of open sets is an open set. So let me give you an example of that. So what if we wanted to show, let's just say, for example, I don't know, 5 comma infinity is open. right? And what do we know? We know any set of the form, any open interval of the form a comma b is open, provided that a and b are finite, right? We know this one, we proved this one. The problem is b over here is finite. Our b over here goes all the way up to infinity. But that's no problem because I could write this interval as a union of finite of intervals with a comma b where a and b are finite. How do I do that? Very easy. So I do 5 infinity, and that is equal to 5 comma 6 union 5 comma 7 union. Well, how did they do it? A plus a, yeah, so the same thing. So 5 comma 6 union 5 comma 7 union 5 comma 8 union, and then you keep going. Yeah, I'm recording. Yeah, thanks. I think, yeah, it's recording. Thanks for that reminder. Okay, so in other words, here's 5, here's 6, here's 7, here's 8. So the first one is this open interval, 5 to 6. Then I'm unioning with 5 to 7. Then I'm unioning with 5 to 8, and so on. Okay, and we keep going. So if you want to, we could write this in a nicer way. We could just say that this is the union as n goes from 1 to infinity of 5 comma 5 plus n. Okay, and now this is your A and this is your B. And notice what are A and B? A and B are now finite numbers. So it falls under this this result. So these are open sets. And this is the union. So remember, it doesn't matter how much you union. Countable, uncountable, finite, it doesn't matter. Once you union in open sets, you get an open set. Therefore, the original guy is open. Okay, so in a similar way, you can show that not only open intervals a, b are open, what we just showed there is a comma infinity is also open. And in a similar way, you could do the same sort of construction to get minus infinity up to a. So this is also open. And minus infinity, infinity is also open. Why? Because this set here, this is just the real numbers. Okay, and we know that the real numbers is an open set. Okay, so all these open intervals, okay, whether it's bounded or unbounded, all these open intervals are open sets. Okay. So the next remark is the interval. So now we are closed at A. Okay, so we're closed at A. So closed at A up to infinity and minus infinity up to A, but it's closed at A. These are not open sets. And the reason for that, remember, to show us that it's not open, all you have to do is find just one point in it that is not an interior point. So you see, now we are including the endpoint. We are now including A. That's the problem. A, the point at the end, at the edge of the interval. Later on, we'll give these points a special name. We'll call these the boundary points. This point A is not an interior point. Okay, so we have found a point, it's A, that is not an interior point. You cannot wrap an interval or a neighborhood around this endpoint such that it completely falls within these sets. Okay, so this set is not open because we have found a point that is not an interior point. So the half open, the half open intervals are not open. Okay, so all of these guys, these are all open. Okay, what we're saying there is that these sets, I think you all call them half open or half closed or something like that. Even if it's like minus infinity up to A, or let's say A up to infinity, these sets are not open. Okay, these sets are not open. Why? Because these points here these points here are not interior points. Okay, these points here are not interior points.
All it need for like interval not to be considered open is one of the points, one of the endpoints not to be open.
Yeah, exactly. Not just an interval, any set. The moment you find any set, so if you have any set, let's say A, back over here. So if you look at this point here, Y, if I try to, so now if you think about it, so this is in 2 dimensions, but the case for 1 dimension is the same thing. If we try to put any open ball, open neighborhood around this point Y, right? You see, it doesn't matter how small I make this radius, part of this set or part of this neighborhood is going to fall outside of it. Okay, so half of it is always going to fall outside. So in this case, it's not open. Oh, sorry, this point Y is not an interior point. So this point Y is not an interior point. So I can write that as Y does not belong to the interior of A. Okay, so now if Y was a point of A, if Y was an element of A, then this set A will no longer be open because I have found a point belonging to that set such that it is not an interior point. This is the condition we are checking, right? So not just for intervals, any set, right? Any set. That's how we do it. Okay, so in a similar way, we know that the neighborhoods, remember, we could always write a neighborhood as an open interval. So the neighborhoods n of x comma epsilon, these are all open sets. But what about the deleted neighborhood? Now remember, the deleted neighborhood is just the neighborhood and you remove the center. Okay, so the neighborhood, so here's our center x, here's our radius epsilon, so here's x plus epsilon, and we need to go epsilon in both directions. Here's x minus epsilon. So this entire set is what we will represent as neighborhood, center x, radius, epsilon. Now the deleted neighborhood is the neighborhood, but you throw away the center. So you see the center, you throw him away. So you just get from minus epsilon up to x, and then what you do, you jump over x. So picture it as you're jumping over x, and then you go from x up to x plus epsilon. So what they're saying there is that the deleted neighborhood, right, and we denoted by n with a little star above. Well, I could write this as the union of these two open intervals. So from the diagram, you could easily see it, x comma epsilon up to x, but I leave x open. Okay, I don't want to include x, so I leave that side open. And then I union that with x all the way up to x plus epsilon. All right, and what do I know about these two sets? These two are open intervals, so therefore these two are open sets, and I am unioning together. Remember, once you are unioning open sets, you are always going to get an open set. So not only is the neighborhood an open set, but the deleted neighborhood is also an open set. Okay, so that's what this result is saying. Now, we know that the intersection of finite number of open sets is open. But what happens if we intersect infinite number of open sets? Do we also get an open set? And the answer is no. So here's a good counter example of that. What if I take sets of the form an, which is minus 1 over n, 1 over n? And what if we intersect these guys together? So anytime you see a set like this, it always helps, if possible, it's not always going to be possible, but if possible, it always helps to draw a little picture of what this set, of what these sets look like. So the set is an, and it's given by the open interval, right? So all of these guys, because they are open intervals, these are all open sets, okay? So when n is equal to 1, this is just minus 1, 1. When n is equal to 2, this is minus a half, a half. when n is equal to 3, this is minus a third, you get the idea, right? You get the idea. So this is, let's say, minus 1, 1, right? So this guy is a1. Then it's minus a half. So this guy is a2, right? And you see how we are slowly closing in around 0. It's a minus a third, right? So we're slowly closing in around 0. Okay, so all of these are my ANs. So what happens if you intersect all these guys together? Now remember, all of these are open sets. So if you intersect all of them together, well, remember, what is the intersection? The intersection is the set of points that is contained in all of them. So from the diagram, there's a rigorous proof for it, but we just need a diagram for now. So from the diagram, it's kind of easy to see that 0, right, is the only point that they will all have in common. Okay, so in other words, if I intersect all the ANs as n range from 1 to infinity, that is just going to be 0 alone. The set containing 0 alone. These are what are called singleton sets. Singleton sets, right? Singleton just means they contain one element. In this case, it's just 0. So these sets are not open. Singleton sets are not open sets, right? So what do we do here? We took an infinite number of open sets and we intersected together and got a not open set. So this is a good counterexample to show that the arbitrary intersection of open sets may or may not be open. We don't know. But if you do finite number of intersection, you are guaranteed to get an open set. Yeah, so that's what this result is saying. Okay, so this is sort of like a summary of everything we've done with respect to the open sets. So we initially started with the idea of what a neighborhood was, and we used the neighborhood to define what are known as the interior points. Those are the points where it is possible to put a neighborhood around it such that that neighborhood is completely within that set. So from the neighborhood, we went to the interior points of the set. And once we figured out which points are the interior points, that now allows us to define what are known as the open sets. So from an interior point, we were then able to define what are the open sets in R. We saw some examples of open sets that we can use to build more open sets. Now remember how to build open sets? Well, you have two recipes. You could take any union and you will get an open set. Or you could take finite intersection and you will get another open set. So once you have some open sets, you could start building together more and more open sets. Now, the collection, and they use this fancy T or the script T, of all open sets of R or all open sets of a general space forms what we call the topology of that space. For us, the underlying set is the set of real numbers, and the topology that we generated in this case was called the standard topology. So there are many different ways you could generate these open sets. For us, how do we generate it? We generated it using the modulus function. Okay, so the set R together with the topology forms what is called a topological space. And topology is a huge area of mathematics where they study all these things. One example of an open set in R was the bounded open interval, AB, right? We know that this is an open set. It turns out that in the real numbers, this is probably the most important of all the open sets in the real numbers. And why is this open interval? Why am I saying this is one of maybe the most important open set in the real numbers? Because it turns out in the real numbers, you can make any open set using these guys. Okay. So it turns out you can build any open set in the real numbers by taking the union or finite intersection of these guys, right? Now the open intervals A, B, you can think of them as forming a basis. So some of you may have met the idea of a basis for vector spaces. This is a different kind of basis. Basis just means in math, they are the building blocks for what you need. So you can think of the open intervals A, B as the basis for the open sets of R. And notice that everything here depended upon our definition of what the neighborhood was. But how do we define the neighborhood? We defined the neighborhood centered at x of radius epsilon using the modulus function, right? This was the set of all points that are a distance epsilon from the center x. So we were using the modulus function to measure these distances. If we came up with a different distance function, and there are many other ways you can measure distance that you may meet later on, then our list of the open sets might change. So you might generate what is, we say you may generate a different topology on the space. All right, so when the modulus function is used as a distance function in R, the resulting topology, now topology again, just a fancy word that means the collection of the open sets. So the resulting collection of the open sets that gets generated from it is what is known as the standard topology, so the usual topology. Okay, so that is the idea of the open sets. Okay, any questions so far with respect to the open sets? No, we're good. Okay, so now we're going to go into the closed sets. So we have open sets, and now we're going to talk about the closed sets. And over here is where a little bit of confusion starts, mainly because many students at this point, and rightfully so, they think that if a set isn't open, then it's closed, right? If something is not open, then it has to be closed. But it's very different when we talk about sets, and we'll see that in a case. Yeah, so now that we've looked at the interior points and open sets, we're now going to turn our attention to what are known as the limit points and the closed sets. And one of the main goal of this entire chapter is to get to the rigorous definition of what is a limit point. And the reason for that is because remember I told you all that this course, Intro to Real Analysis 1, is like the rigorous foundation of what you may have done in your first year calculus, which was take derivatives, take limits, integrate, talk about series and sequences and those sort of things. But the central idea in your first year calculus course was the idea of a limit, right? And it turns out that, well, I know all of you probably have a rough idea of what a limit is. You're getting closer and closer to something, but you don't actually reach it. So we want to define rigorously what it means by you're getting closer and closer to something, but you don't reach it. And it turns out that not every set you could actually do this. So not every point is a limit point. We'll see that later on. So you can't just take limits at x approaches any point. It has to be a certain type of point. Yeah, so I put here the most common mistake made is this statement. So this statement is wrong, by the way. So that's why I put mistake. So this is the most common mistake that I see people making at this point. They say, okay, if a set is not open, then it must be closed. Or if a set is not closed, then it must be open. So these statements are wrong, right? These statements are wrong. So don't take this one. So we'll soon see that when it comes to sets, we could get all these possible combinations. We could find sets that are both open and closed at the same time. We could find sets that are not open and also they're not closed. We could find sets that are open and not closed, and we could find sets that are closed and not open. So when it comes to sets, anything goes with respect to this. You could find any combination of this. And you should at least have one example in your mind of each of these cases. Okay, so you should have like a typical example of these things in your head, at least by the end of this chapter. So now we want to define what are the closed sets. Now there are many different ways, and depending upon the textbook you read, there are many different approaches for how to go about making this definition. All of those different definitions are all equivalent to each other. It just depends on the approach that author or whoever, or whatever textbook, it just depends on the approach that they are taking. The approach that we are going to take is we are going to define a set A to be closed if the complement of it is open. Okay, so again, we are using the idea of the open sets now to define what it means to be closed. So if I want to figure out if a set is closed, what do I need to do? I don't look at that set. What I do is I look at the complement of the set because I know what it means to be open. Every point is an interior point. So if I want to check whether or not a set is closed, don't look at that set. What you need to do is take the complement of it and then ask yourself, is that set open? If that set is open, then yes, the original guy is closed. If that set is not open, then the original guy is not closed. Okay, so let me write that for you. Right, so the way we are going to go about defining our closed sets, and like I said, there are many different ways. If you search it up on the internet or if you look at different textbooks, they might define what a set to be closed. For example, if it contains all its limit points, or if it contains all the limits of sequences in it, or all these different, there are many different ways you can define what a closed set is. For us, we are going to define what a set to be closed using the idea of the open set. So we say that A is closed if the complement of it is open. So if we take the contrapositive of this, remember the contrapositive, if P implies Q, the contrapositive means not Q implies not P, right? And these two statements are equivalent, right? They are logically equivalent. It means they mean the same thing. Okay, so take the contrapositive of this guy. So that is saying A complement is not, so I negate both sides, not open. I'll write it this way. Right, so I'll write it this way. If A complement is not open, then A is not closed. Right? So if the complement is not open, then the set is not closed. If the complement is open, then the set is closed. Right? You all will get used to it. Don't worry. Okay, so what are some examples of these closed sets? So what about the half open interval? A infinity. Is this closed? So remember again, to answer the question, at least for now, until we introduce more results, but from the definition, to answer the question, is the set closed? What we need to do is look at the complement. So what is the complement of half open interval A infinity? Okay, so here is, so it's half open interval A infinity, right? So let's just say here is A, and these are all the points, including A, all the way up to infinity, right? So that's what this is. So the complement of it is just the points that are not in this set. Okay, so it's all these points. So I don't include A. So here is, so this is A, right? This is A, and this guy here is A complement. So A complement is just minus infinity up to A, but I don't include A because A was included in the original set. So if I want the complement, The complement cannot have A. So this is an open interval. So therefore, this is an open set. So the complement of A is open. Therefore, A must be closed. Okay, so the half open interval turns out to be closed. And in a similar way, if you do minus infinity up to A and you include A, that is also closed. The closed interval, so think back in high school where they told you if you do these square brackets on both sides, they told you that is what is called a closed interval. But they probably didn't tell you why, what does it mean to be closed? Why closed? Where is this name coming from? The reason why this type of interval is called a closed interval is because it is closed. Okay. So let me just draw that for you. So we know that these intervals, A, B, which are called the open intervals, right? Again, your high school teacher didn't tell you why they are called the open intervals. They are called open intervals because they are open. So what about these intervals where we close both ends? Again, your high school teacher told you that these are called the closed intervals. But they didn't tell you why they are called closed intervals. Well, now I'm here to tell you. They are called closed intervals because they are closed sets. So here's A and here's B. Now to see whether or not, or to see why this set is closed, look at the complement. So the complement is everything outside of the set. So from B, go all the way up here. So this is just B all the way up to infinity. And from A, but I don't include A because A is included in the original set all the way down. So this is minus infinity to A. So the complement of the set, complement is the union of these two green sets. So it's minus infinity up to A union B up to infinity. And this is open, and I'm unioning. Remember, once you are unioning open sets, you are guaranteed to get an open set. Okay, so the complement is open, therefore the original set must be closed. Right? So the complement is open, the original set, the thing that you took the complement of, must be closed. Right? So closed intervals are closed sets. Right? So that's why they are called closed intervals. Singleton sets now. So a set with one point in it. So for any real number x, if you take just the set containing that real number, remember these are what are called singleton sets because they contain a single element. These sets are closed. Again, why are these sets closed? Just look at the complement. So if this set is just the element x, right, and you are in the real numbers, then the complement of it are just all the points to the left of x. So that's minus infinity up to x, union all the points to the right of x. That's x up to infinity. So these are the union of two open intervals, and open intervals are open sets. Union of open sets is open. Okay, so the complement is open, therefore the original set is closed. So right away, we have a good catalog of these closed sets, right? Half open intervals, closed intervals, singleton sets. All of these are closed sets, right? Singleton sets are closed. Now, what about the so now we're going into the common sets of numbers, natural numbers, rational numbers, integers, irrational numbers. What are these sets? It turns out the natural numbers, the counting numbers, are closed, right? So let me draw the picture for this one. And they are closed for the same way singleton sets are closed. Okay, so here is 1, 2, 3, 4. Okay, we're trying to answer the question, or we're trying to show that the natural numbers is closed. So again, in order to see whether or not the set is closed, I need to look at the complement of it. right? So the complement of it so the natural numbers are these integers, right? The 1, 2, 3, 4, and you keep going. So the complement of it are all the spaces in between, right? So it's this guy go all the way down. So this is minus infinity up to 1, and I don't include 1. It's this part here, so it's between 1 and 2, but I of course do not include 1 and 2 because those are natural numbers. It's between 2 and 3, right? So what's in green here, this is the complement that I'm drawing, right? This is the set we need to look at, 3, 4, right, and so on. You get the idea. So it turns out that the complement of this set, I can write it as minus infinity to 1 union. So now I'm just writing the green, the set in green. 1 comma 2 union 2 comma 3 union 3 comma 4 union. You get the idea. Okay. And what are all of these sets? Well, these are all open intervals, and you know all open intervals are open sets, right? All of these guys are open sets, and it is a infinite union, right? In this case, it's denumerable. It's countably infinite union. But it doesn't matter. Once you are unioning open sets, you will get an open set. So this set here, this set is open. And if the complement of a set is open, then the set must be closed, right? So the natural numbers is closed. So the moral of the story is, right now, until we introduce any other result, the moral of the story is, if you want to figure out whether or not the set is closed, don't look at that set. Look at the complement of it and check whether or not the complement is open or not. Okay, so the natural numbers is closed. Now, in a similar way, the integers are also closed, right? Because the integers are just the natural numbers, but you include the negative version of them and you throw 0 in. So that is also closed by the same reasoning. You can write the complement of the integers as all of the intervals between the integers, right? So the integers are also closed, right? What about the rational numbers? Okay, so recall that the interior of the irrational numbers is empty, right? So the irrational numbers is not open, therefore the rational numbers is not closed, right? Remember I had this result up here. So we are using this. If the complement is not open, then the set is not closed. So what are they saying there? They are saying since the irrational numbers, which is Q complement, we showed this in the last section when we were studying open sets. So you need to go back and look at that. Why are the irrational numbers not open? So since the irrational numbers is not open, okay, so just following what I have highlighted here, then the rational numbers is not closed. Okay, so the rational numbers are not closed. And in a similar way, the irrational numbers are also not closed. Right? So the rational numbers are not closed. These have open intervals. So the half open intervals where they are unbounded. So one of these are infinite, are closed. These are not closed. Let me show you that one too. Okay, so these half open intervals. So a to infinity and minus infinity to a. So these half open intervals are closed, right? Because their complements are open. However, if instead of the endpoints being infinities, what about these? If I do a b or b a, again, these are type of half open or half closed intervals. These guys are not closed. Okay, these guys are not closed because write their complement, and you will see that their complements are not open sets. right? So these are closed, but these are not closed. And Q and Q complement are not closed. Okay, they are also not open, right? They are also not open sets. What about the open interval? So the open interval we know is obviously open, but there's no reason why the open interval can't also be closed. What if the open interval is also closed? Okay, well, what about the complement of it? So the open interval AB, the complement of it is just all the points to the left of A, that you include A, union all the points to the right of B, and you include B. So this set, the complement, is not open. It's not open because, for example, if you take A is in the complement. A is not an interior point of the set because if you try to put a neighborhood around A, half of it is going to fall outside. Okay, so if you try to put a neighborhood around A, so A, B, the complement, I'll draw in green. So the complement will include A, and the complement will include B, right? So the complement is minus infinity up to A, but includes A, union B to plus infinity. That's the complement, right? So is this green set open? Well, take E. Take the point E. Here it is. That's the point E. Start putting neighborhoods around this set. So if, for example, you take this neighborhood around this point E, does this entire neighborhood fall inside of the green set? No. Look, half of it is falling outside of this set. So this part here is not in, for example, this piece, right? So therefore, A is not an interior point of the complement. Okay, so the complement is not open. Therefore, open interval AB is not closed. Okay, so many sets that are not open are not closed. Okay, any questions so far? Right, so if you have any questions, you could also type it in the chat and I'll take a look at it as well. Okay, okay, everything good so far. So when you're reading this back over the carnival weekend and you're studying, what you could do is make a table, right? And that will help you see everything together in one page, right? So here's the table that you should try to make. So this table will be of examples, right? Examples. You will put some examples of open sets, right? And you will list out some. So for example, the empty set, the real numbers, open interval A, B, right? These are all open sets. You'll put an example of closed sets, right? So these are closed interval A, B. We'll see in a bit, these are also the empty set and the real numbers. Half open intervals where one side is unbounded. Oops, minus. Right? So these are some examples of closed sets. The natural numbers are closed, the integers are closed, sets that are not open. Okay. So sets that are not open are the rationals and the irrational numbers. The half open intervals where one side is bounded. These are not open sets. Even these guys, closed interval AB is not an open set. Right, so you list some more. So what you want to do is list out how many and try to think about each time you list a set, think about why it's not, why these are examples of it. And what about not closed? Not closed set. So again, I claim that irrationals and irrationals are also not closed. Open interval AB is not a closed set. So I'm looking at for sets whose complement is not open. So right, so not closed. Oh, sorry, yeah, not closed. So the half open intervals are also not closed, where one side is finite. A, B, close, open. Right, so these are also not closed sets. Right, and you could think of some more. Right, so think of some more. So this is a table that you should look at and think about. If you could look at each of these sets and see why they are open, why they are closed, why they're not open, why they're not closed, then you will understand pretty well the idea behind the open sets and closed sets. So something I just want to point out right away from this table is that you see here that the rationals and the irrationals are both not open and not closed. Okay, so if you're looking for an example of a set that is not open and also not closed, you could choose any of these, the rationals or the irrationals. Also, a next thing to look at, if you're looking for a set that is both open and closed, these are the only two. The empty set and the real numbers are the only two sets, at least for the standard topology. The empty sets and the real numbers are the only two sets that you could find that are both open and closed at the same time. Okay, so from this table, you can have some examples of these things. And how do I know? So we proved, or we looked at previously, why the empty set and the real numbers are open sets. But why are the empty set and the real numbers closed sets? So that's given by this term, right? So this term is saying that the empty set and the real numbers are closed. It's also saying something that might look a bit familiar. It's saying that the intersection of any collection of closed set is closed, and the union of any finite collection of closed set is closed. So we saw something like this previously, where they were talking about arbitrary unions and finite intersections. Right, let me go back to that. We saw something like this for open sets. So this is the theorem for open sets. What are they saying? They are saying the empty set and the real numbers are open. Okay, let's go to this one. They are saying the empty set and the real numbers are closed. Okay, this term is saying that the union of any collection of open is open. What's this one saying? This one is saying that the intersection of any collection of closed is closed. So you see they're sort of reflections of each other, where the unions turn to intersections and the opens turn to closed. And the reason for that, well, the proof is left as an exercise, but I'll give you all the hint. The reason for that, why this term here and this one for the open sets seem to be like complements of each other, is because in order to prove this theorem, the one for the closed sets, you need to use the one for the open sets. So you need to use this theorem for the open sets. And what you do is you just take the complement of these things. Why do you take the complement of it? Because what is the relationship between an open set and a closed set? A set is closed if the complement is open. So that's why if you take the complement, for example, of the second one here, you get this one here. Okay, so again, what you should do is sit down and maybe write something like this, where on one side you have the open sets, and on one side you have the closed sets. So this one is saying that empty set and the real numbers is open, or are open. Empty set and the real numbers are closed. Okay, this one is saying that what was it? The arbitrary union of open set is open. The closed counterpart to it is the arbitrary, so the union turns into intersection. Intersection, open turns into closed. So the arbitrary intersection of closed set is closed. And the third one for the open set was the finite intersection of open is open. So now take the complement of it. So we are taking the complement of it. So C for complement, right? Take the complement of it. So finite intersection changed. So finite changed the, sorry, intersection changed the union. So intersection change the union. So you get finite union of closed set is closed, right? The arbitrary intersection of closed is closed, finite union of closed set is closed. So I think these are analogies that students usually use to remember these things. Although after a while of thinking about it and you do enough questions, it becomes obvious after a while. But for now, if you need these things, here it is. So once you are dealing with the closed sets now, once you are dealing with the closed sets, as long as you are intersecting closed sets, it doesn't matter how many you intersect. As long as you are intersecting closed sets, you will also get a closed set. However, if you are unioning closed sets, you are only allowed finitely many to get a closed set. Okay, so that means that there must be a counterexample. Right, so I put here, how does this result compare to the unions and intersection for open sets? And this is the table you should have in mind. So let me write here what C is. C is for complement. Right, so take the complement and you get that. Of course, this is not the actual proof of it. You'll sit down and write out the actual proof of it. This is just how you should visualize it if you need to. And also I put here that the empty set and the real numbers are both open and closed. Are there any others? It turns out for the real numbers in the standard topology, that is what we are working with. These are the only two. There are no others, right? It has to do with a property called connectedness, that we'll meet later on, but these are the only two for us. And the rationals and the irrationals are neither open nor closed. So now again, the question is, are these the only two? Or could you find other sets in the real numbers that are not open and not closed? So think about it. For open and closed, only two. Empty and real, only two. But what about not open and not closed? Are there only two? Is it only the rationals and irrationals? So think about that. We'll talk about that later on, right? Okay, so that brings us to now we want to essentially look at something called the nested interval theorem. So for that, I need to first tell you what it means for sets to be nested. Okay, nested just means you find one inside the previous one. So if you have a collection A, so the collection is written by this fancy, which is script A. So this is a collection of non-empty subsets of R. We say that this collection is nested if an plus 1 is a subset of an. Okay? Or equivalently, if am is contained in an whenever m bigger than n. Okay, so the definition looks complicated, but once you see the diagram, you'll be like, okay, it's very easy. So this is A1. So let's say right now that one. A is nested collection. Right, so A1 is this set. All that means for a collection to be nested is that A2 is now contained in A1. Right, so here's A2. A3 is contained in A2. Here's A3. A4 is contained in A3, right? And it keeps going down. So you get the idea, right? It keeps going. So n plus 1, the n plus 1 is contained in the first one, the one before it, into the n1. Or the other part of that definition, what I was saying, equivalently, m is contained in an whenever m is bigger than m. Where did they get this from? So, say we didn't know this. How could we figure this out easily? Take, for example, this one and this one. Okay, so A1 and A3. Which one is contained in the next? A3 is obviously contained in A1. Okay, so this is your M, this is your M. So in this case, 3 is bigger than 1, right? 3 is bigger than 1. So M is bigger than M. Right? So now just remove these guys and rewrite it in terms of M and N, and you will get exactly this. Right? So it says that AM is contained in AN whenever the number M is bigger than N. In other words, they are sort of decreasing. Right? So these are what I call a nested collection of sets. Right? Nested collection of sets. So for example, yes, I have here. So A1 is the biggest, right? A1 is the biggest, A2 second biggest, A3 third biggest, and so on. Now the collection doesn't terminate, right? The collection keeps going, right? It keeps getting smaller and smaller. Now the question is, what happens if we intersect these collections? So sometimes this is called a nested sequence. Sometimes it's called a nested collection. Sometimes it's called a decreasing sequence of sets. Any word is fine for you to use. So this is a theorem. It's called the nested interval property in R. The proof I put here left as an exercise. Although the proof is fairly complicated, you can look up the proof. The proof is in the Battle. So that's one of the reference texts, Introduction to Rate Analysis by Battle. You can look up the proof in there. Really interesting proof. So what this one is saying is if you take now, so the definition of nested, notice that they didn't tell you what the set AN could be. They could be any sort of set. The nested interval property is telling you, it's telling you that you're taking a nested collection, but the sets are intervals. So in other words, each interval is contained in the one before it. So let this be a nested sequence of non-empty closed and bounded intervals in R. Then the intersection is non-empty. Okay, so that one is saying, what if we have intervals? So the intervals look like this. So here is I1. Here is I2. So remember, if these are nested collection or nested intervals, then I2 is contained in I1, and I3 is contained in I2, and I4 is contained in I3, and it keeps going, right? So that's I2, maybe I3, and it doesn't have to be centered around any point, by the way, right? It doesn't have to be centered. Maybe I3 is there, maybe I4 is here, right? And it keeps going in. What that is saying, what that nested interval property is saying, if you intersect all these intervals together, the intersection is non-empty. In other words, there's at least one point in this intersection. In fact, you could show from the proof that not only is the intersection not empty, it is only equal to a single point. There's only one unique point of intersection in all of these intervals. That's this calculus when you intersect them, right? And what are the conditions? 3 conditions. The first one, IN must be nested, right? Each one must be contained in the next. The second one is each IN must be bounded, right? Bounded means the endpoints of these intervals are finite. So what is an example of an interval that is not bounded? This one, minus infinity to 5, let's see. This is not bounded, right? Not bounded. So the intervals must be bounded. And what was the third condition we see there? The INs must be closed. Right? So in other words, the closed and bounded intervals, well, once we are in the real numbers, the closed and bounded intervals, we know exactly what those look like. Those look like this, A comma B. So each of these INs, they look like this. So if you want to, you can index it by N. AN BN is equal to IN. Right now we see later on that this condition of something being closed and bounded in the real numbers is equivalent to something called compact. Right? It's equivalent to, we'll see later on what it means to be compact. This is the property of the compact sets. Right? So like I said, the proof is left as an exercise, but maybe have a look at it before you want to attempt it, because the proof is kind of complicated. So it's called a nested interval property in R, and it's used to prove many other things. And if you're looking into this one, maybe you could also look into, if you want to look into this, you can look into the Cantor set. The Cantor set, right? Look into something also called the Cantor set, and what happens, we'll see what happens with the Cantor set. Okay, so finally we made it to to the limit point. This is what we were after all along. So let me give you the intuition behind the limit point. So we're going back to first year calculus, right? And we're taking limits now. And we will write something like the limit as x goes to a of something equal to something, right? We don't really need the other parts. This is what we are interested in. The limit as x goes to a. Right? So here's A, and intuitively, we kind of know what it means for X to approach A. It means that we are moving closer and closer to A from either the left or either the right. So we are taking points closer and closer to A. But remember, the whole idea of a limit is you are taking points closer and closer to A, but you are not allowed to take A, right? X cannot be equal to A. That's the whole idea that makes a limit work. You take points arbitrarily close to A, but you don't take A, right? So this is the idea of a limit. So what we want to make precise is, first of all, what it means to take points arbitrarily close to A, or what it means to get closer and closer without reaching A. The second thing we want to look at is, can we always do this? If I give you any subset A is a subset of R. If I give you any set A, can you, and I pick any point in A, can you always approach this point such that there will always be other points of A arbitrarily close to it? So the thing is, all these other points you see here, they must also belong to the set A, by the way. I don't know if they told you that in calculus. Maybe not, because it wasn't important then. But when you say X approaches A, these X values must also be points of A. They must also belong to A. So given any set now, given any set, if you take any point in that set, can you, and you put a neighborhood around it. If you take any point in that set and you put a neighborhood around it of some radius epsilon. Epsilon could be really big, epsilon could be really small, you don't care. You put a neighborhood around it. Can you, here's the question, can you always find another point in that neighborhood that belongs to the set A? Is that always possible? So this is the question we want to ask ourselves. If it is always possible to do this, no matter how big or how small you make this epsilon, if in every single neighborhood around this point A, you always find points of the set, big A, then we say A is a limit point of the set. These are what the limit points are. Limit points, so here's how we think of limit points. Limit points are points such that if you wrap a neighborhood around it, no matter how big or how small you make these neighborhoods, you are always going to find points of that set somewhere in there. In other words, so think of it like you're trying to filter out points of the set A. You're trying to filter out these points. If you have a limit point in there, it is impossible to filter out points of A from it, right? You can't separate them out. Okay, so how to so that's the rough idea of what these limit points are. How to make all of this precise, right? So epsilon delta definition. So let A be a subset of R. A point X belonging to R is a limit point, sometimes they are called the accumulation point, of the set A. If so, here's the definition. Every deleted neighborhood of X contains a point of A. So right away, couple things. A point X is a limit point. Where does X have to belong to? So they just say X belongs to the real numbers. So first thing about a limit point, the limit point may or may not belong to the set. So the set we are talking about is capital A, big A. The limit point is X. X may or may not belong to A. Notice they said X belongs to the real numbers. They didn't say X belongs to A. So right away, so now you'll learn about two different types of points, the interior points and the limit points. For an interior point, that point needs to belong to the set. For a limit point, it may or may not belong to the set. We don't know, we don't care, right? Whether or not it belongs to the set or not doesn't concern us if we are looking for the limit points. Okay, so a point X belonging to the real numbers, it may or may not belong to the set, is said to be a limit point of that set if, second subtle part of this definition, every, not just neighborhood, deleted neighborhood of X containing a point of A. Why are they taking deleted neighborhood and not just the regular neighborhood? You see, the reason why they are taking the deleted neighborhood, what is the difference between the deleted and the full neighborhood? The deleted one just removes the center. What is the center of the deleted neighborhood of X? The center is X. So they are saying here that every deleted neighborhood of X contains a point of A. That's a fancy way of saying every neighborhood contains a point of A except X. You are not allowed to choose X. Right? For example, yeah, sorry, let me write it back. If I told you that so A is a subset of R, and I told you that the point A actually belongs to the set, actually belongs to big A, right? Actually, let me use the notation that they were using there. Right, so they use X. So X, well, here's X. So if X belong to A, then if I take any neighborhood about X, any neighborhood, any epsilon neighborhood, of course that neighborhood will contain a point of A. It contains X. X is a point of A. So it doesn't matter if the point belongs to the set, then every neighborhood will contain a point. It will contain the center, X. So we want to avoid that case. We don't want to choose the center because it may be X may or may not belong to the set. So I want to throw away X. I want to throw out X. I say when I'm looking for these limit points, when I wrap a neighborhood around this point, I want the point of A, let's call him, that will be this little guy, A. So this guy belongs to A. I want that point to be different from X. I don't want to keep choosing X. Okay, so how to say I want that point to be different from X? All I have to say is that A belongs to the deleted neighborhood, right? Because the deleted neighborhood does not contain X. Okay, so that's why they are saying the deleted neighborhood, because I don't want to choose the center, right? The center isn't of no concern to me. That's why I was saying that in the idea of a limit, you are getting closer and closer to a point, but you don't actually reach the point. This is the part that they are encoding. they don't actually, how do you encode, don't actually reach the point, don't take that point. How they are encoding that is they are saying take the deleted neighborhood. If you wanted to allow yourself to choose that point that you are approaching, then you will take the full neighborhood. But I don't want to take that point, so I take the deleted neighborhood. So that's the set, that's the next thing here. Okay, so that's what a limit point is. But how we want a way to write this a bit more rigorously to use in our proofs. Okay, so here's how to write it. For every epsilon, the deleted neighborhood of that radius centered around the limit point x intersect A is non-empty. What does it mean for this intersection to be non-empty? It means in this deleted neighborhood contains a point of A, right? If you are in this intersection, you are in the deleted neighborhood and you are also a point of A. So that's why they're saying the intersection is non-empty. Now, just like before when we were studying the interior points, we collected all the interior points and put those together in a set that we call the interior. So in a similar way, we are collecting all the limit points together and throwing those into a set. The set of all limit points is called the derived set of A, and we denote it by A prime. So the set of all limit points is called A prime. Now, remember I said that that the limit point may or may not belong to the set. So if x if x is an element of A and it is not a limit point. So if you have a point of A, okay, let's do it this way, right? So this is your set A. X belongs to A, right? X may or may not be a limit point. X is a limit point, is not a limit point. If X belongs to A and is a limit point, then X belongs to the derived set, right? That's what it means to be a limit point. You belong to the derived set. If X is not a limit point and it belongs to the set, X is said to be an isolated point. And why is it called an isolated point? It's very easy to see from the diagram. So suppose that the set A, let's just say is 0, 1, union 7. Let's just say this is set 0, 1, union 7. So here's 0, here's 1, here's 7. I claim that 7 is an isolated point. How to see that? So first of all, let's check the condition to be an isolated point. Does 7 belong to A? Yes, 7 belongs to the set. Is 7 a limit point? So in order for it to be a limit point, every single neighborhood you throw around 7 should contain at least one other point of A. You are not allowed to choose 7. Why are you not allowed to choose 7? Because the neighborhood is a deleted neighborhood. So for example, what if I do this neighborhood? What if I go 1 epsilon equal 1? So what if here's 8 and here's 6? Okay, so what if I throw a neighborhood around 7 of radius 1? Right, so I'm looking at the interval 6 to 8. What other points of A are there in this interval? Well, the only point of A is 7, but you're not allowed to choose 7. 7 is the center. You're not allowed to choose the center as your point. So in this neighborhood, we have found a neighborhood, an epsilon, such that the deleted neighborhood centered at 7 of radius 1 has no points of A in it. Therefore, 7 is not a limit point, right? If it was a limit point in this neighborhood, I should see a point of A somewhere in there. There's no other point of A in there. So 7 is not a limit point of this set, right? So 7 belongs to A, is not a limit point of A, Therefore, 7 is an isolated point of A. Now look at the diagram. Do you see why they would call these points isolated points? Where is the majority of the set? Look, most of the set is over here, 0, 1, 0 to 1. And then you have this point, then you have number 7 all here by himself, all alone, isolated from the rest of the set. So that's where the word isolated comes from. They're all the way, by themselves there, right? So these are the isolated points. So if you belong to the set, if you are a limit point, then okay, cool. If you're not a limit point, then we call you an isolated point, right? So 7 is an isolated point. So these are what I call the isolated points. So a lot of new definitions that you will hopefully sit over your long weekend and think about limit point, derived set, isolated point, all these things, right? So a limit point of A may or may not belong to the set. How is this different from an interior point? An interior point must always first belong to the set, right? An interior point must, first of all, the point has to belong to the set. If the point isn't in the set, then you can't even ask if it's an interior point. It has to belong to the set. So a limit point, it doesn't matter. Take any point, right? It may or may not belong to the set, doesn't matter. It could still be a limit point. Okay, so that's the main difference between limit points and interior points. Okay, so what is the relationship between this? So this is only for R, by the way. Well, you're probably not going to come across any other topology. So, but in general, this does not work. This is mainly for subsets of R. So this result is saying, so first of all, if I'm looking for limit points, right? So now the question is, I gave you a set, A, and I want you to find the limit points for me. Where are you going to look? This theorem is telling you that all the interior points, that's what this A with a circle above it, these are the interior points. All the interior points are also limit points. So for any subset, so what that result is saying, that is let A be some subset of the real numbers, right? That result is saying if X is an interior point of A, then X is a limit point of A. In other words, X belongs to the, so I'm using the second notation, okay? Both these notation mean the same thing. If X is an interior point of A, this implies X belongs to the derived set. X is a limit point, right? So how do I prove this? Well, how do you prove X is a subset of Y? You take any point in X and you show that you can find it in Y. The idea is the same. I want to show, required to prove or required to show, I want to show the interior is a subset of the derived set. So I take any point in here and I need to show it also belongs to there. Okay, so let's see how to do that. So suppose X is an interior point. What is my goal? My goal is to show it is a limit point. Okay, if you are an interior point, what does that mean? What is the definition of an interior point? It means that there exists some radius, so we're going to call this radius delta, such that the neighborhood around X of that radius is entirely within A. This is the definition. This is the definition of an interior point. Now, for a limit point, I need to show that for every single radius around X, this is only one of them, right? Delta is only one of them. For every single radius, all the other radii that you choose, you could always find a point belonging to the set A in that deleted neighborhood. Okay, how to do this one? So let epsilon be any radius now. Either epsilon is less than equal delta or epsilon bigger than delta, right? That's the only thing. If epsilon is less than or equal to delta, then, so what I need to do now, I need to show that I could find a neighborhood centered at x of radius epsilon that contains a point of A different from the center, different from x. How do I do that? So I take two cases. The first case, if this radius that I choose is less than or equal to delta, okay, then the deleted neighborhood centered at x of that radius. So the deleted neighborhood, you know, is always contained in the full neighborhood, right? The deleted neighborhood is always a subset of the full neighborhood because the full neighborhood is the deleted neighborhood with the center. And what do I know about the neighborhood centered at x of radius epsilon? Well, epsilon is less than delta. So the neighborhood centered x of radius epsilon is a subset of the neighborhood centered x radius delta, right? That's something when we were talking about neighborhoods. Here's x, um, what was it? Epsilon less than delta. Epsilon less than equal to delta, right? Here's delta, right? So here's x plus delta, x minus delta. Here's epsilon, so here's x plus epsilon, x minus epsilon, right? So from here to here, this is the neighborhood centered x radius epsilon. From here to here, this is the neighborhood centered x radius delta. What is the relationship between these two? Which one is subset of which one? Right, so clearly the neighborhood centered x radius epsilon is subset of neighborhood centered x radius delta. And we know that the deleted neighborhood is always subset of the full neighborhood, right? So all you have to do is look at this one and this one. So ignore him. Oh, okay. That just deletes it. Okay. So ignore this one in the middle, right? Ignore that one in the middle. So from this, I get the deleted neighborhood, center x radius epsilon, subset of neighborhood, center x radius delta. Intersect both sides with A. Intersect him with A and intersect him with A. Okay. What do I know about this intersection? If so remember that the neighborhood center x of radius delta is subset of A. So if I intersect this guy on both sides with A, then this guy is contained in A as well, right? So this guy here is contained in A, right? So I have a neighborhood contained in A. So therefore it must be non-empty. Right? Let's go back to this and we'll see it. So you see they intersect both sides with A. So you get the deleted neighborhood intersect A is equal to the neighborhood. Okay, why is that equal to the neighborhood? Let me see it over here. Right? So the deleted neighborhood how to show this? Okay, let me do it this way. Let's just say this is just at A, right? A may or may not be an interval. Let's just say that's just at A. This is X. What do I know? I know that the neighborhood centered X radius delta contained in A because X is an interior point of A, right? So here is delta, X plus delta, X minus delta. right? So clearly, this neighborhood contained in A. Now, what am I taking? I'm taking epsilon less than or equal to delta. Right, so right away, you probably already see the idea. So here's epsilon, so here's x plus epsilon, here's x minus epsilon. So this guy here is the neighborhood centered x of radius epsilon, right? So what is the relationship now between this neighborhood and the set A? Look at the diagram, which is inside which? Then clearly the neighborhood centered x radius epsilon is contained in A, right? And the deleted neighborhood is contained in the neighborhood. So the deleted neighborhood is also contained in E, right? So therefore, if I intersect the deleted neighborhood with A, well, the deleted neighborhood is already in A. Okay, so remember from your set theory, if X is a subset of Y, then X intersect Y is what? Here's Y. Here's X. What is X intersect Y? It's just X. So this is your X, this is your Y. X is a subset of Y. Therefore, what is X intersect Y? X. So from that, what is X intersect Y? It's X, right? It's X. So that's where they're getting this result from, right? It's X. So X intersect Y is X because this guy was contained in A. And the neighborhood, the deleted neighborhood is obviously non-empty, right? Because it's a union of two intervals, and you of course know from back when we study the intervals that the intervals are uncountable. So this has uncountably many sets in it. So what have we showed? We showed that for any epsilon, if that epsilon is less than or equal to delta, then X is a limit point of A, right? Then the neighborhood into the deleted neighborhood intersect A is non-empty. That is what we are after. Now, what about the second case? What if the epsilon that I have is bigger than this radius? I can't use this, so what am I going to do? Well, if the epsilon is bigger than delta, then the delta, so now epsilon is the bigger one, right? So the neighborhood centered on x of radius delta is contained in the neighborhood centered x of radius epsilon. Epsilon is the bigger one now. So remove the center. So remove the center and you still get the same subset relation. So the deleted neighborhood of delta is subset of deleted epsilon neighborhood. Then intersect both sides with E. Okay, intersect both sides with E. Now the left-hand intersection. What do I know about the left-hand intersection? This deleted delta neighborhood intersect E. Remember, the delta neighborhood. Let me go back to the diagram. Where's this delta neighborhood? This delta neighborhood is in E. Right, this delta neighborhood is in A. So what about the deleted delta neighborhood? That's also still in, right? That's also still in A. So therefore, the intersection of the deleted delta neighborhood and A is non-empty, right? So the delta neighborhood is in A, so the deleted delta neighborhood is in A. So the intersection of the left-hand side, that's the side, the intersection is just given by the deleted delta neighborhood. So the deleted delta neighborhood is a subset of the right-hand side. And this deleted delta neighborhood, how many points are in here? So we know that the deleted neighborhoods, they are open sets. They are the union of two intervals. Intervals contain uncountably many numbers. So this deleted delta neighborhood is non-empty. Obviously, it's non-empty. It contains uncountably many real numbers. Okay, so you have a non-empty set contained inside this set. So this set on the right-hand side must be non-empty. Okay, so what do we get again? Again, we got that the deleted epsilon neighborhood around the point X intersect A is non-empty. That is the condition for a limit point. The limit point means once you take any epsilon radius about that point, the deleted neighborhood intersect the set is non-empty. There's at least one point of A in this neighborhood. Okay, hence, for all epsilon, for all radii that we choose, we can construct a deleted neighborhood of that radius centered at X such that when we intersect it with A, the intersection is non-empty. This means X is a limit point of A. Right, so altogether, what do we start with? We start with, suppose X is an interior point of A. And what do we show? We show that X is a limit point of A. So therefore, the interior is contained in the derived set. So I put here, try to prove this theorem using the contrapositive. That is, if X is not a limit point, then X is not in the interior. Okay, so I suspect this proof might be a bit easier than this one. So try to do this second proof and see if it really is easier than this first one. So is it true? Right, so we know from that, so we just showed that the interior is subset of the derived set. This is true. The question is, do we get the converse? Is the derived set subset of the interior? And the answer is no. No, this is not true. In general, this is not true. How to show this is not true? Well, you need to get a set A such that the set of limit points is not contained in the interior. So do I have any example? Yeah, I do have an example. So what if you take A as open interval AB? Okay, open interval AB is an open set. So the interior, if your set is open, you are equal to its interior. So the interior is AB, right? And well, what are the limit points of this set? It turns out every point of this set will be a limit point, right? So this is subset of the derived set. But I claim that the limit points of AB, open interval AB, is not contained in AB, right? So what was the set? The set A we are given is open interval AB, right? So since this is an open set, we know that the interior is equal to the set, so the interior is open interval AB. The question is, what are the limit points? So I claim that the derived set is closed interval AB, right? So if we want to check this, is this true? What is A prime? A prime is closed interval AB. What is the interior? Open interval AB. Is this a subset of this? No. So you see, this is a good example to show that in general, the derived set may or may not be subset of the interior. In other words, all you have to do is find a limit point not contained in the interior. So why is A a limit point? Right? Or why is B a limit point? Right? A and B are limit points of A, which are not in the interior of A, since they do not belong to A. Right? So you need to sit and think about why are A and B limit points of this set. Okay. Yeah, so why are A and B limit points of this set? So I'll show you all of it and we'll end class there. So again, if we just think about what the set looks like, so this set is open interval AB, right? So we know why every point is an interior point, okay? Because you could always wrap a neighborhood around it falling within the set. The question is, for example, why is B a limit point of the set? Well, take any neighborhood around B, no matter how big or how small. So take any epsilon neighborhood around B. Can you find a point in open interval AB? So you're looking for any x in open interval AB inside this neighborhood? Yeah, look how many points. Take any one of these points. All these are points belonging to open interval AB inside this neighborhood. And what do we need? We need just at least one. We just need 1 point of the set inside this neighborhood. So I know you're seeing like half of the neighborhood falling outside, right? And you're thinking, but half of the interval or half of this neighborhood isn't even inside the set. No, for limit points, that doesn't matter. It doesn't matter for limit points whether the neighborhood parts of it fall outside the set. Most of the neighborhood could fall outside the set. That doesn't matter. All we require is that we could find at least 1 point of that set somewhere in this neighborhood. We don't care if the neighborhood falls, part of it falls outside of the set, part of it falls inside the set. We don't care. We just need at least 1 point of that set falling within the neighborhood somewhere. Okay, so B is a limit point of this set of open interval AB. In a similar way, A is also a limit point of this set AB, right? So therefore, the set of all limit points, right? We know that all the interior points are limit points, right? We just proved that. That's what we were proving up here. Oops, where is it? Yeah. All the interior points are limit points. So it's the interior of this set. It's the interior of this set. Union AB. What's the interior of open interval AB? It's open. So it's AB, union, AB. How to write this set? That's just closed interval AB. Right? So that's what the derived set is for this guy. Okay, so sit and think about it over your long weekend. And we can discuss it further next week. Okay, are there any questions?